This is Chapter 3, Plate Tectonics, Lecture 1. And in this chapter is where we really start to get into some important parts of geology. Until now, I've kind of glossed over the mechanism for a lot of the processes on Earth. We'll actually get into it now. So the goals for this chapter include an exploration of the main features on Earth. We'll look at the distribution of earthquakes, volcanoes, and mountains and see how those connect. We will introduce the theory of plate tectonics and look at 3 types of plate boundaries. We will investigate how plate tectonics explains various features and is consistent with the data that we have. So this is, of course, a map of the world, and we have various enlargements of different parts of the world. We have the Pacific Northwest, South America, the South Atlantic, the Arabian Peninsula, Japan, and Tibet. Let's start with the Pacific Northwest. What we have here, you can see a step in the seafloor connected to a ridge. There's also a chain of volcanoes in western North America, the Cascade volcanoes. That was a bit abrupt. I didn't want to be done yet. There's a linear feature that's parallel to this step in the seafloor as well. They're not just volcanoes here. We have quite a few high peaks in line with this area. All right, South America. We have a elevation high on this portion of South America and an oceanic trench. That's this dark part within the ocean, the Pacific Ocean. These are the Andes. In the center, we have low relief, so not a lot of change in elevation between points between here and here. We have a continental shelf on the east coast. And this side, of course, has many volcanoes in the Andes. All right, South Atlantic Ocean. So this is between South America and Africa. What we have here is a ridge located along the center of the ocean. That's the Mid-Atlantic Ridge. And then we have zigzags that actually mimic the shape of these adjacent continents. Ridge, and then as you go away, you get a smooth, deep seafloor. And I'll point out these continental shelves here and here, and the zigzags in the ridge. Those are fracture zones, actually. All right, highest elevation on Earth is in this area with Mount Everest. This is called the Tibetan Plateau. It's the highest plateau on Earth. The Himalayan range runs along the southern edge of the plateau right here. And this is India. Most of India is low in elevation with this abrupt rise in elevation. And because of that, a lot of local winds and weather is affected by the fact that you have a low area that is up against a high area. All right, we'll go now to Japan. A lot of different features here compared to what we've seen before. So Japan is located along these curving ridges and trenches. These are mostly below sea level. Let's see. So curving ridges up top, these are the high points. And then oceanic trenches, the dark points. You may know that Japan has frequent earthquakes. It has volcanoes that are still active, like Mount Fuji. All right, we'll transition to the Arabian Peninsula. It's flanked by the Red Sea. The Red Sea is a narrow, moderately deep sea. It has a trough in the center. It's a rift. This area has been pulled apart. Now the Persian Gulf is shallow. It lies between Arabia and the Zagros Mountains of Iran. And this, of course, is Africa. It has a triangular area called the Afar region right here. These are kind of out of order. Persian Gulf, Afar region. There's an oceanic ridge right here as well. This shape matches the corner of the Arabian Peninsula, so that's an observation. What is our interpretation of this? Were these once together? Yes, they were. All right, now back to a world map. We can see some of the main features on a whole here. Remember the oceanic fracture zones that we pointed out near the Pacific Northwest? In this area, we have linear island and seamount chains. That's raised area. Some of them are sticking out of the ocean. That would be the Hawaiian Islands. A lot of them are below the surface of the ocean. We have deep ocean trenches, like along the coast of South America. We have mid-ocean ridges here. Oceanic plateaus. Those are actually high points beneath the surface of the ocean. And then, of course, continents. Just point them out. They exist, right? Submerged ridges and island arcs near Japan. Huge continental shelf north of Europe. Plateaus like the Tibetan Plateau. All right, we're zooming in on the mid-ocean ridge. We can compare the shapes of the continental edges on opposite sides of the Atlantic Ocean. This figure is not in the book, but that's all right. It's a simple world map. These things kind of look like they might have fit together at one point. If we cut these out and pasted them together, we could find that the corner of Brazil matches the indentation in Africa. The East Coast curves in, Africa curves out. There's something here. So some continents have shapes that fit together. That's our observation. Shapes of the continents match across the Atlantic Ocean. South America being joined with Africa, Antarctica surrounded by Africa, India, and Australia. An interpretation would be that continents fit back together because they were once joined and they later moved apart. That's a continental drift hypothesis, but we don't have a mechanism for that yet. We just observe that and we interpret this, but why and how? Well, with that, there's the fossil record, okay? And scientists have found fossils of land creatures found on continents. Those continents are now separated by oceans, okay? So you found this guy here and here, this guy here and here, but now these continents are very far apart. So what happened? An interpretation would be that once these continents were joined so that these creatures could just easily walk from one place to another. But the ones that are extinct now, they can't. Everything's different now, right? And uh, this theory of continental drift explains our observations without any explanations of land bridges connecting things over, thousands of miles. We don't even have to think that way. It's just perhaps the continents were once joined and now they're not. But how? And more evidence for this. Um, if you look at our continents, there were a few different ice ages throughout geologic history. Um, One observation made was that these continents have glacial features such as scratched rocks. Glaciers move across the rock and they scratch the rock in a specific direction as they move. But we're matching these various scratch marks, to put it very simply, but they no longer line up. If we put all the continents together again, they might just line up. Say when the continents are restored, we could say the ice sheets moved in predictable directions away from the center. So that's some evidence that perhaps the continents were together and now they're apart. But with continental drift alone, okay, there's a problem. When scientists first started talking about this, it seemed to make sense, but there was no viable mechanism at the time to say how these continents moved away from each other through the oceanic crust. And that was because when this theory was first introduced, it was done so by scientists in the northern hemisphere. And they were unfamiliar with southern hemisphere data. And so continental drift on its own was rejected for lack of a mechanism to explain how it worked. Let's just look at the data that we have now. This isn't every earthquake that ever happened. This is some data of earthquakes, occurrences, their epicenters, where they occurred throughout our planet. Some observations are that they occur in belts. We see them like mountain belts. We see them along mid-ocean ridges. We see them along trenches. Mountain belts again. Some regions really don't have earthquakes. We see a ton of them along the Tibetan Plateau. In all the areas that we explored at the beginning of the lecture. We can also look at this pattern of volcano occurrences, like where they are really. These orange triangles. We see them in the belts. We see them at some mid-ocean ridges, oceanic islands in the middle of the Pacific. That would be Hawaii. We see them in mountain belts next to trenches, the Red Sea in East Africa. And again, they're sparse in some regions. We see them a lot in these island arcs next to trenches as well. Now let's just look at elevation. So these darker areas, it's brown mostly, those are the high points. They kind of match where we see earthquakes and volcanoes. Most parts of our continents are fairly low in elevation. We have mountains and belts. We have some mountain belts next to trenches, and of course around southern Eurasia and the Tibetan Plateau is quite high in elevation. East Africa as well, in the Afar region, is quite high. So if we take all that, we have the distribution of earthquakes in yellow, volcanoes being orange, triangles, and high elevations in brown. That's kind of covered up by the other data. And we also have a plate tectonics map. I want to say right now, earthquakes, that's EQ, volcanism, or the building of mountains, we call that tectonic activity. We have these belts of tectonic activity that divide our lithosphere, our upper earth material, into tectonic plates. All this evidence was used in the theory of plate tectonics, which isn't that old. It's come about largely accepted in the 1970s. So, again, not that old of an idea in its current form. But it's based on these data and these occurrences. And with that, we have a tectonic plate map. And you see arrows on that? That's the relative motion of the plates that we're able to track. Tectonic plates move relative to one another. There's 3 types of relative plate motions. When tectonic plates move apart, that's a divergent boundary. When they move toward each other, that's a convergent boundary. And when they move past one another horizontally, that's a transform boundary. We use this, and hopefully the colors look right to you. Yellow being divergent, red being convergent, and green being transform. This is what your book has. Let me know if you have any trouble, say you're colorblind and the colors don't look right. We can talk about it. There's other forms we can look at. But we can compare these locations with mid-ocean ridges, oceanic trenches, mountain belts, and then lines of islands. Okay, so this is a mid-ocean ridge. It has divergent boundaries, but accompanying that you have, as these are pulled apart, transform boundaries form. This red along South America is a convergent boundary. We got a divergent boundary here along Mexico and a transform boundary in the western United States. Nothing on the East Coast, right? Nothing in this part of South America. Convergence all throughout this area. And then a transform boundary here. So we're noting that. Zooming in on divergent boundaries. This is the mid-ocean ridge. We'll have to talk about it. This is where oceanic plates move apart. We call that seafloor spreading. It forms new oceanic crust as the plates spread apart. And the shape of the mid-Atlantic ridge mimics the shape of continents on either side. So the ocean is newly formed as seafloor spreading moved these continents apart. Talk about features and processes of mid-ocean ridges. The center is a narrow trough or a rift. It's formed by spreading and faulting. The solid asthenosphere rises to fill the gap, and it melts as it rises. Magma rises through fractures formed by spreading. And then some magma does erupt onto the seafloor, and some solidifies at depth and forms new oceanic crust. The ridge is higher than the normal seafloor because rocks are hot and dense and the lithosphere is thinner in that part. If you want, you can sketch this. And we'll stop here for today and pick up with continental rifting, pulling apart.